Hello and welcome. This is the next Edexcel FP1 video. In this video we're continuing with our topic of matrices or matrices, whatever you want to call them. Okay, and in this one we're going to be looking at what we mean by the identity matrix. We're going to be using that to be able to work out something we call the inverse matrix, and I'll be giving you a few hints and tips as we go along, and then at the end of the video I'm just going to put a quick summary on the board. Okay, it's one of them videos where I'm being quite generous, so you can just skip to the end and I'm sure there'll be the summary on there if that's all you're interested in. But as I said, if you're learning this for the first time, then obviously probably a good idea to watch. Okay, so in the last video that I did, we looked, as I said, we looked at adding multiplying matrices together. Okay, and in that video we said they have to be the same size in terms of there has to be the same number of there has to be the same amount of numbers in the first row of the first matrix. Okay, as there has to be the same amount of numbers in the column of the second vector. Okay, so if it's 3, 2, 6, 5, 7, 1. Okay, you would have to times that by something that had at least 3 columns. Okay, so that could be 3, 2, 1 and 7, 2, 5. Okay, so you might want to times those two together, and what we said is you do the column of the first column of the second vector times each row of the first vector. And when I call it vectors, I did it in the last video, it's because they look like vectors. They're not. The matrices. I do apologise. Okay, so it's the first column of the second matrix times all of the rows of the first matrix. Okay, and then you do the second column of the second matrix times all of the rows of the first matrix. Okay, and then when you put it in your answer matrix, okay, you put column 1 times row 1, and the first column is all to do with column 1, so column 1 times row 1, column 1 times row 3, etc, etc. And then you would do column 2 times row 1, column 2 times row 2, column 2 times row 3, and then the next column would be column 3, the third column of this times the third row of this if there was one, and you would go on and on. Okay, so that's a little bit of a recap of multiplying them together. Okay, and obviously when you add and take matrices, all you're doing is adding and taking like parts. Okay, so hopefully you all know what I mean by that, or you know, at least one person does anyway, then that'll be alright. So in this video what we're looking at is as I said, the identity matrix. That's the first thing we're going to be looking at. So what do we actually mean by an identity matrix? Well, it's almost like, you think of it, times it. It's like a factor of the matrix, factor of 1 of whatever matrix it might be. And the key thing to specify with this, the identity matrix is exactly the same. It doesn't matter what matrix you're looking at. Okay, well, in a 2x2 obviously, it doesn't matter what variation of a 2x2 matrix. Okay, it could be 7, 5, 9, 2 or 8, 1, 2, 5. It doesn't matter. Okay, as long as it's a 2x2 matrix, this remains exactly the same. Okay, and what matrix it says it's a factor of 1. Okay, so you could think of it, so if we've got this matrix big A, okay, and it's made up of A, B, C, D, okay, when we do the matrix of A times the identity matrix, that is the same as doing the identity matrix times the matrix A, and that I mean, it seems logical. Okay, in any other situation you go 3 times 2 is the same as 2 times 3. Well, yeah, sure, but when we multiply a matrix out, we maybe do the column of the second matrix times the row of the first one. So obviously doing it a different way around would give us a different answer. Okay, so we have been lied to about that as well. Right, okay, so that's kind of a weird situation, and also when you multiply them together it's the same as the original matrix. Okay, it's the same as matrix A, so that's why, as I said, it's a factor of 1, and that kind of helps you to remember it. Alright, so I'll just give you this matrix and then we'll prove it. Okay, the identity matrix, we'll obviously call it I, is 1, 0, 0, 1. Okay, so it's 1, 0, 0, 1. So when you multiply them together, you should just get A, B, C, D, okay? And you can kind of work that out, alright? So remember, so column of the first column of the second matrix, the first column of the identity matrix times the first row of the matrix A, okay? So it's 1 times A, so top left is A, plus 0 times B, which is obviously just 0, okay? So it's A plus 0, which is A. So that's your top left, okay? That's column 1 times row 1, column 1 times row 2. So 1, 0 times C times D, okay? So 1 times C, which is obviously C, and 0 times D, which is obviously 0, okay? So it's just the same. Top right, okay? So that's column 2 times row 1. So it's 0, 1 times AB, okay? So it's 0 times A, 0, and B times 1, B, okay? So it's just B. And then your bottom right in the answer matrix is column 2 times row 2. Okay, so it's 0, 1 times CD. Okay, so 0 times C, 0 plus D times 1 is D. Okay, so you can quite clearly see that is the same as matrix A. Now, isn't that amazing? Well, it's just logical, really. If you multiply it out, you can see where we got that from. Okay, so that's the identity matrix. Now, so that's the identity matrix. That's just, as I said, that identity matrix of 1, 0, 0, 1 is exactly the same to any 2 by 2 matrix you're looking at. Now, I said the identity matrix, you can almost think of it as a factor of 1, okay? Just 1, really. Because obviously it's only got 1, it's not got 2s and 3s, so you can think of the factor of 1 if that makes some kind of sense. If it doesn't, then, you know, stuff you. Okay? Right. We're going to look on something called the inverse matrix. Now, the way to think of this is, obviously I know this is different because this is trig and not matrix, but it's the same as sine x equals whatever it might do, and sine of the inverse sine of x. Okay, it's the same principle. Okay, in other words, you can think of them cancelling each other out. Okay, because obviously if you did the sine inverse of sine, or if you did the sine of the inverse of sine, you would just be left. They would cancel out. Okay. So, as I said, the identity matrix is a factor of 1, okay? So therefore, if we do the matrix of A times the inverse of matrix A, okay, so let's call this the matrix A, and we'll do the inverse in a minute, work it out, that will give us the identity, because it's like doing sine x times the inverse of sine x. You're just going to be left with 1, okay? Well, obviously not 1, but you get the idea, alright? So essentially they cancel out. So the matrix of A times the inverse of the matrix of A is the identity matrix, okay? So we're going to prove that a bit later on when we work out what this inverse matrix is. Now, you may go, well, you've just given us an equation there for the identity matrix, and obviously we could rearrange that, okay? So the inverse of the matrix A to the minus 1 is equal to the identity matrix over A, or the matrix A. Well, no, maths isn't that simple. We don't have so far we don't have a rule for dividing two matrices together. We have a rule for adding and timesing and subtracting, but we don't have a rule for division. Okay, so obviously we can't use that, that's quite clear. So we have to do something else to work out the inverse of A. Okay, so if you want, okay, so what you would do, now the first thing I'm going to do actually before I start this, we need to work out something called the determinant. Alright, and to be able to work out the determinant we need to understand a few things, and I'll explain why we need to work it out in a minute. Okay, so we've got two diagonals here, okay, so we've got B and C, they're diagonals, and A and D, they're also diagonals in this matrix. Now, one of them is the trailing matrix, and one of them is the, it's going so well as well, one of them is a trailing matrix, and one of them is a leading one of them is a trailing diagonal, one of them is a leading diagonal. And A and D, so A times D, is what we call the leading diagonal, because you can see it starts high if you want to think of it like that, so it's a leading diagonal. And C and B, okay, they are what we call C times B, that is the trailing diagonal. As I said, you don't really need to know that. It won't actually go state the trailing diagonal. Okay, so the determinant of A, sometimes known as det bracket A, okay, is essentially the sort of the difference between these two. So it's the leading diagonal take the trailing diagonal. Okay? So that's what the determinant of A is. It's the leading diagonal take the trailing diagonal. Sorry for the spelling there. So, how does this allow us to work? Obviously that's A times D, by the way. That's quite clearly A times D take B times C, or C times B, whatever. Alright, okay. So, how does that enable us to work out the inverse of the matrix, okay? Well, as I said, this is just another formula that you need to know. Alright, so the inverse of A matrix is 1 over the determinant times, now this is going to get where it gets a little bit, the determinant of A, this is where it gets a little bit weird. Basically, what we're going to do, we've got a matrix up here, and what we do is we times it by the opposite of the leading diagonal. So we switch A and D around, so D goes in the top left, okay, and A goes in the bottom right, okay, and we also times that by the opposite of the trailing diagonal. In other words, it's the negative of it, okay? So top right is negative B and negative C bottom left. Okay, so obviously you've got a value for 1 over the determinant of A. One of the ones that I did, you got a 10, okay? And obviously that would work out, then you would just times, it ended up being the this weird matrix thing, okay? Times a scalar, which is obviously just the matrix, so you can times out the individual terms. Remember, we're not times it by another matrix, so it's nothing too complicated. Now there's one thing that I want to say at this point. Now this determinant of A, we assume it's either going to be positive or negative. As I said, it doesn't really matter if it's either one. Obviously you will get a different answer, but don't be put off if you get the determinant of A to be negative. However, this determinant of A, quite clearly, it could potentially be 0 if the leading diagonal is equal to the trailing diagonal. Obviously the determinant of A will be 0. And if the determinant of A is 0, we do 1 over 0 times, it doesn't matter what this matrix is, it's going to come out to be undefined, okay? Because obviously 1 over 0 is undefined. So if the determinant of A is 0, okay, in other words, if the leading diagonal, so if A times D is equal to B times C, if it equals 0, okay, if that holds true, then what we have is, obviously we won't have, whatever matrix is being considered at that point, we won't be able to find, there's no way in this crazy world that we live in, that we could potentially find the inverse for this matrix. So in other words, there isn't one, okay? If the determinant equals 0, there's no inverse matrix of whatever it is we're looking at. Okay, so therefore we call it a singular matrix, because it only exists on its own. There's no inverse of it. There's no other, obviously there's other matrices, but there's no other matrices which are related to that. So no inverse, so it's on its own. Okay, so that's why we call it obviously the singular matrix. There you can quite clearly see the link. Alright, so that is pretty much what we do. That's all the information, all the bits of what you need to know. Okay, so I'm going to fit a question on there. I'm going to need to do some rubbing out. I'll try and fit another question on there. Oh, another question, a question. Okay, so you could come up with any question you like that's a 2x2 matrix, okay? And apply this thing. So really, these 4 bits of information that I sort of put in boxes, they're what you need to know, okay? Alright, so these 4 boxes, if you were to do a summary, okay, you would just do a summary of them 4 boxes, okay. At the end I'll put that on like the page so the people who've skipped right to the end, the lazy bones, can obviously get there. Alright, so that's the 4 points that you need to understand really, and obviously you can note these down as well if you want, but if you just remember that, and you can note these down. Okay, so as I said, you could come up with any question that you would like, obviously. And then if it was 0, you would have a singular matrix, alright? So you shouldn't be put off if you don't get a positive number for the determinant of A. Okay, so obviously we know the identity matrix, well, that doesn't change. So in essence, that's just something you need to commit to memory. Okay, that the identity matrix is 1 0 0 1. And if you just remember that, you can apply that to this. This is really, if you forget that, you're pretty stuffed. Alright, so as I say, it's just a case of doing questions, using that and remembering it. Okay, so if we've got a matrix A, we'll call matrix A, and we'll do it 3, 2, 7, 9. Okay, and we want to find the inverse matrix. Okay, and sorry, we want to find we want to find the inverse matrix. Now, as I said, we do have the identity matrix, but obviously I'm not going to write that in my answer because it's at the top left. Near the top left of the voice is going again. The top left of the page. Okay, so there's no point me writing that out again. But obviously, if you were writing this as an answer, you'd obviously write it in. Okay, so the first step that we would do is work out the determinant of A. So for any question that's like this, obviously it probably won't be as simple, but you do the same method for each thing. Okay, you work out the determinant, you sub it in the formula, so rearrange this, rearrange the matrix of A, okay, and sub it in there. Okay, so what you could do at this stage is write what A, B, C and D are if you're committing this to memory. Okay, and if we were to do that, obviously A would be 3, B would be 7, C would be 2 and D would be 9. Okay, so you could correspond it to that, but as I said, you don't have to. Okay, so the determinant of A, so det A, is equal to the leading diagonal, take the trailing diagonal. Okay, the leading diagonal being 3 times 9, or in other words, A times D, and the trailing diagonal, C times B. Okay, so 2 times 7. Okay, so it's 3 times 9, take 2 times 7. In other words, it's 36, take 14. Okay, so we can put that as equal to 36, take 14, which is 22. Yep, just have to think of that for a second. Okay, so the determinant of A is 22. Now, as I said, this might get a bit messy because I've just done this off the top of my head, so you may need a calculator for this. So obviously, therefore, if we were to sub this formula in, so we know the determinant of A now, we just sub it in the formula, so the inverse of the matrix A is equal to 1 over 22, or the determinant of A. Okay, now you could put 1 over 3 times 9, take 2 times 7, but it's just easier to put 1 over 22. And then we work out this matrix. Okay, so the top left is D, we said D was 9. Okay, and the bottom right was A, which is 3. Okay, so we've swapped 3 and 9 around. Okay, it's always good to put commas there. And take the negative of 2 and 7, so bottom left is negative 2, top right is negative 7. Okay, so now it's just a case of expanding this out, really. Okay, so it's 9, so the inverse of A, okay, is 9 over 22, and then it's negative 7 over 22, top right. Bottom left is negative 2 over 22, obviously you could cancel these down, but I'm giving you the raw figures. And then bottom right is 3 over 22. Okay, and if you wanted to if you weren't sure that was right, you would times it by the matrix A, okay, the original matrix, and it should give you 1 0 0 1. Okay, so obviously the matrix A is 3 top left, 2 bottom left, 7 top right, and bottom right is 9. Okay, so when you expand that out, it's A times the inverse. Great. Oh, that's not. Imagine these are swapped round, okay? I do apologise, I haven't done it right. So it's crucial the way you do it round, okay? This is one of the things that obviously I was pointing out. So it's the column of the inverse of A times the row of A, okay? So the column of the inverse of A is 9 over 22 and negative 2 over 22. So you could label it as what I normally do. So it's column 1, column 2, and then of A it's row 1 and row 2. So you know what you're timed in and what you're not. Okay, so the first one is column 1 times row 1. So it's 9 over 22 times 3. So is that... Yeah, I do apologise, sorry. I was just thinking I was going crazy. Okay, so it's 9 over 22 times 3. So obviously it's 9 times 3 over 22. So it's 27 over 22. Okay, and you add to that 2 times negative 22 on 2. So in other words, it's take 4 over 22. And that obviously gets you, great, done that right. Checking I've not done something wrong. So, great, I've not made a mistake here, have I? I think I've, oh great, for God's sake, this is because I've done it the wrong way around. I do apologise, please completely ignore what I've just said. So it's a column 1 of A times row 1 of, so it's the column 1 of the inverse of A times row 1 of A, so I do apologise. So it's 9 over 22 times 3, so that is 27 over 22. And then it's 7, okay, times negative 2 over 22, which is obviously take 14 over 22. What? Oh my god, I'm getting this wrong, aren't I? Have I done that right? Yeah. So, sorry, anyway, I'll just shut up because I'm probably making some easy calculation mistake. So it should come out to be 1001. Okay, so that, I'm not sure. I think I've done some calculation error there, so I do apologise. Yeah, that hasn't gone well. I do apologise about it again, but so there's nothing I can really do. I've already kind of put this on the video, so you just have to. I mean, I might edit it out, I might not. I'll see what happens. All right, so just gonna rub that out, and then obviously you can copy. If you've not, you can copy this already, and we're going to move on and do, well, not move on really, we're going to do put some more questions up, and I'll go through some more to kind of make up for that if I've not going to edit it out. Okay, so I'm just going to rub all that off and put some more questions up. Welcome, this is the sort of carrying on from where we were. Now, as I said, there's a question on the board that you can have a go at there, working out the inverse matrix. Okay, I've sort of started you off there by kind of giving you a hint on what to do. One thing before, or if you've already had a go at it by already pausing it, then it's fine, obviously. But just before I go through the answer, I just want to say that it doesn't matter. I don't know if I made a huge mess up before. I was going to say something else there, but you could stop myself. The fact that I've put that the matrix A times the inverse matrix is equal to the identity matrix, which is 1, 0, 0, 1. It doesn't matter which way round you have the A. Okay, so it can be the inverse of A times A equals the identity matrix, or A times the inverse of A, or inverse of A times A, is all of it's equal to the identity matrix. Okay, so if you've not already paused it and had a go, please do. If you haven't, if you already have, then you just have to wait a second or two. Okay, so then people can have a go at pausing it. Alright, okay, so hopefully you've come back. Well, we'll say hopefully you've come back. You're all listening to this if you come back, stupid pleb. Right, okay, so the first thing you would do is work out the determinant of A. Okay, now if you relate this to A, B, C, D, okay, we said the determinant of A was the leading diagonal, which in other words, minus 1 times 2. Take away negative 4 times 3, okay, which is obviously minus 2 take away negative 12, okay, which is therefore obviously just 10. Alright, so that's the determinant of A. Now we just applied the determinant of A to this inverse A formula. Okay, so the inverse of A, okay, is equal to 1 over the determinant of A, in other words 1/10. And you rearrange this, okay, so you swap the 2 and the minus 1 over, okay, so you get 2 in the top left and minus 1 in the bottom right. And you just take the negative versions of minus 4 and 3, okay, so your bottom left is just 4 and your top right is minus 3. Okay, so now it's just a case of expanding this out. Okay, so in other words, it just becomes equal to top right is 2/10, and then it's negative 3/10, right? And then its bottom left is 4/10, and the bottom right is negative 1/10. Alright, and now to prove that is, if it asks you to prove that is the identity matrix, it said, sorry, not the identity, if it asks you to prove that that was in fact the inverse matrix, okay, you would just sub it into this formula, okay, and obviously you could either pick, you would just put in the matrix A, and you'll find out inverse matrix, and you times them together, should get you your identity matrix, okay. So if we did that, I'm saying it doesn't matter which round you put it, so the first one I'm going to put is the matrix A, which is -1, -4, 3, 2, okay, and we times that by 2/10, so -3/10, 4/10, -1/10, okay, and then it's just a case of times in the second matrix's first column by the first row in the first matrix, and then the first column in the second matrix times the second row in the first matrix, and then doing the same but for the second column, the second matrix. Okay, so then we just have our answer matrix, which is obviously column 1 times row 1, so it's negative 2/10 times 1, which is obviously negative 2/10, and then you add 12/10 to that, 3 times 4/10, which obviously gets you 10/10, which just gets you 1, okay. And then below that we have column 1 times row 2. Yeah, so it's 2/10 times -4, okay, plus 4 times 2, okay. And obviously they cancel out, so you just get 0. So it's 8/10, negative 8/10 plus 8/10, which obviously gets you 0. And then the top right is column 2 times row 1. Okay, so it's negative 3/10 times -1 plus 3 times -1/10, okay, which obviously 3/10, take away 3/10, which obviously 0. And then column 2 times row 2, so negative 3/10 times 4, plus negative 1/10 times 2, which is obviously 10/10, in other words 1, okay. So therefore that proves it's equal to the identity matrix. Now, I'm not sure if I put it in before, I'm going to leave it in or edit it out, but that previous one I did, if it's still in there, or if it's not, you can ignore what I'm talking about. I think I just made a mistake, okay, in my calculations, because the method was right, alright? So that works every single time for a 2x2 matrix, okay? So as I said, that identity matrix that we've put at the top right there, well, the middle even, that is always the case, okay? So just need to commit that to memory, and we'll see these 3 things as well. It's just a case of repeating this with different questions and putting it in your brain, really. There's nothing else more to it than that, okay? Standard kind of revision practice. Okay, so thanks for watching, and hopefully, you know, you've been able to understand that, and sorry if I've left the edit mess in there, but hopefully it wasn't too bad. And if the focus has been off, I do apologise as well, but, you know, that's what these things happen. Right, so thanks for watching, see you next video. Sorry, just one more thing actually. I know this is a weird angle, but just you have to leave with it. I would just should have said, if you have any questions on what I've done, okay, so if you have any questions on any of the work that we've got on the board there, please do let me know, put in the comments below. And if you have any questions on, you know, like this that you can't work out, please do leave them in the comments below, or message me on my Facebook page, which is obviously Bill7187 Facebook page, and I will get back to you, okay, and I will produce a YouTube video or whatever, okay, and obviously talk you through the answers. Okay, so thanks for watching, and sorry about putting another little side thing to this. Alright, so we'll see you in the next video or something.